Hello everyone, it's September 19th. Wasn't able to do it early because I have some class to take, so let's do it now. It's kind of late. That's alright. We can handle this. Alright, another string related question. Given two string S and T, return the number of distinct subsequences of S which equals T. Subsequence formed by deleting some things without disturbing the remaining character relative positions. Subsequence of this, while AC is not. But to guarantee the answer fits on the 32-bit signed integer. So rabbit and a rabbit. So we have three ways you can generate a rabbit from S. Removing this, removing this, removing this. A lot of ways back. So I can remove 1000. Okay. Well, yesterday was DFS. This feels like DFS as well because we only have 1000, so we can afford something ridiculous. Oh wait, yesterday is 100, right? Today is 1000, so not as ridiculous as what we had yesterday. Anyway, so basically we're trying to say removing something from S so that S equals T, right? Or we're trying to match T to S, the longest common subsequence. The longest common subsequence, what we want is the longest common subsequence to be equal to bag, right? And can we modify the longest common subsequence? Like when we find it, let's say like bag, so BA, and then when G will find it, right? But then we B again. Hold on, let me see. Longest common subsequence. Let's say we have going to be a 2D array, and we have BAG. So we have BAG, and then on the top we have BAB, G, BAG. So it's like this. So B and B with matching. This is not matching, matching. No, yes, no, no. And now A and B. Actually, this we can also just match. Alright, so here A and A match. So we're gonna go diagonal. So we say, oh, it's the length, right? So we're recording as the length. So we record length is 2, and this is not. So we're gonna go up and here, pick the maximum one. So it's gonna be 2. Not maximum one. Not. And this is matching. Right, so that will be 2 as well. And then these two are not matching, so it's going to be 2. Yeah, so this will be 2, and not matching will be 2. Matching, that will be 3. So we say BAG, we have BAG, right? And then these are not matching. Not matching. That's also 3. Okay, so if we run the longest common subsequence, we'll get the length, right? And then we find the length is the same. That means we have found. So among the one that we found, we can mark it. Right? We mark another one. It will always be diagonal. Right? Always diagonal. So we say we're gonna have this one, right? And 2, 3, 4. So I have 3. So we just need to find all the possibilities, right? All the possible ways that we can form. So we go here, right? We can go to 2. Right, so we have this way to go to 2, we have 2 ways to go. So we can either go diagonal, or we can go the other way. So we can go this, and then from 2 we need to go to 1, so this one doesn't have, but this one has. Right. So that's one way. And then that's it. So we move on to the next 3. Will it always happen? Yes, it will always happen on the next 3. So we have this one and this one. So both ends. So we have 2 more. Right. So this one will be how do we get here? This is, hold up. Talking about ending here. So it's BA. Hold on. Now that's the last one is G, and then we have this A, and then we can go to the other. No, that's not right. I was playing around with the how can we give back. Like how is this done? Like how do we give back to the thing? Isn't just like going 3, right? So that's when we match. It has to go through the match, right? So we have the match. Let's say here's a match, this is a match, and this is a match, right? And all the ones that we have a match, we just let's highlight all the places that we have a match. Right? This is a match, and this is a match. So these are BAGB. These are the matches, right? So in order to find our way back, we start from here, right? And then we need to go to the second row, right? That has the match. Now we have 2 matches. In the first row, we have 2 matches. Therefore, if we start from here, then the second row we need to find a match. We can pick anyone on the second row, right? And then we on anyone on the first row. Okay? So we start from here. We have 2 choices, right? And then we have this. That's 2. Right? And then we can choose this. That's 3. Right? That's 3. And that's it. And then we choose here. And we can only choose the ones to the left, because we cannot pick the ones go to the right. So that's another one. Is that 4? Is that 5? 1, 2, 3. That's 3. 4. I have 4. Where did the 5th one come from? So I have this as the last BAG. And we have... Oh, there's another match. I didn't see. There's another match. Ah. Hold up. So, are we saying level by level, right? Level by level. I have 3, 4, and 5. Hold up. So what I'm talking about is, think about these are 3 levels. All the levels, right? These are levels. And each level, we get all the index that match it. Each level get all the index that match it. And then we can go from top down, that's fine. And then from top down, first level, the first one, and then we need to find on the second level that whose index is larger than this, and then on the third level, the index is larger than the second level, and we add them together. That will be the results. If we use this as an example, so what we have, so we can first, let's say, get all the index for each character, right? All the index for each character. That could be 0, right? Like, I just suddenly realized if they don't match, then it should be 0. Like, let's just say this. That should be 0. Yep. Okay, so the letters in T, so let's say letter in S, right? So R, we have position is 0, A position is 1, B the position is 2, 3, and 4, and then I the position is 5, and T position is 6, right? That's what we have. And now on rabbit, right? So we have R, A, B, B, I, T. So R, we go through R. So R we now pick out is 0. Now we go to the next one is A. Now A, we can binary search, right? We can binary search because it's sorted. But binary search for the location, the smallest location that is larger than 0, which we have is 1. Next, go to this B. We need to binary search a location that's larger than 1, so we have 2. And then go to the next B. It should be larger than, so be 3. And then I and T. Okay, that's 1. And then once we're done, we go back for each one. Like if I have more T, no more T, I no more I, but B will have more B, right? Because in this B, I start from 3, but actually I have 4. So we branch out, we have 4, right? And then going back to the first B, and I realize the first B we can go to 3, right? And then we'll go to 4. That's three ways. And then coming back, this B no more, and this B will have 1 more, which is 4. And then, but this we don't have anymore, so we abandon, back. Yep, I think that is the solution. So, all right. I think this shouldn't be too hard. Let's see how we do. We don't need deck for this. I think this is just call it. We need a default dict. So from collections, import default dict, right? So we're gonna have pause position because default dict list, right? And then for letter in S, actually we also want to have I letter in enumerate S, right? And enumerate S. What do we have? We have position letter dot append. I, right? So now we can create a dictionary with each letter as its key and a list of positions as its variable. And because we need to use binary search, so we need to say also from bisect, import bisect. Bisect. Let's say bisect. Well, what do we want? We want something that's larger, right? We want something that's larger. We have a index and we have a list of index. We're gonna find the index where to put it, right? Somewhere So I think it's gonna go binary search, gonna bisect right. So that's that. And then we're gonna say for, we're gonna say result equals 0, right? And then for, now we're gonna be DFS, self.result, and that's DFS, right? So DFS is gonna be looking at index, right, which is index on the T, and then uh, I think that's about it, right? That's about it. Just index. Yeah, and that, I know, not return anything. I don't need to return anything. Return none. All right. So we say if index equals len t, then self.rest plus equal 1. Because we go all the way to the end. Else, it's not equal to t, which means we're somewhere inside the t. And now what we do is get the position, right? We'll get a position, and we need a previous position. So we need a previous. So when you say pre-position, right? So we have a previous position. So we have the current, and what do? We say position length so we have the index, right? The index is somewhere here, right? And then we use the index to find the positions, and then we can run binary search on this, right? So binary search. Okay, so bi shall equal to, okay, there's one thing I need to find out. Does binary search, hold on, I need to find out is from bisect, say import bisect, let's say left or right, right? Let's say A is this. Can I do bisect right 1 and say, no, A 1, is that possible? Oh yeah, it is good. It does give you. If it's 0, that means it's no good. So binary index is going to be bisect right position T index, right? So that's the letter, and then preposition, right? The preposition is what we passed previously. The preposition I'm gonna pass in, and I'm gonna run the binary search, and the binary search will give me the position where I need to insert it, which means that's gonna be the index of the actual thing, right? Index of the actual thing. So what I'm going to do is for I in range, that's going to be bi, right? That's going to be the one that's larger, all the way to len position t index, right? So we're going to go from the binary search position all the way to the end. For each one, right? For each I, what we're going to do is we're going to call DFS. The preposition is going to be the position I am taking. Right? The position I'm taking is position T index. Right, that is I. That's the position I'm taking right now, and we're gonna go to the next one. Next one is gonna be index plus 1 because I handle the index. When I go to the next one, and then the position needs to be the next. That's the current position. So the next one we will do the binary search based on this one. All right, so we're gonna DFS and blah blah blah, done, and we're gonna return. No, we're gonna call DFS. What the hell is the preposition? Ha! The preposition is something that we use to do the binary search, right? So the first letter. It's like the current should be larger than the previous one, which is going to be -1 because that's preposition, because the first position on the S is 0, so the preposition would be -1. Honestly, -1, yeah, let's do -1. And indexing start with 0. And we're going to return res. Actually, self.res. Alright, let's check this one. So first have wrap bbbit and this rabbit. Right? So this one result is 3. Second is bab, gbag, and this bag. Result is 5. And we have a test case. Let's just say, I think we do a rabbit and rabbit. This one is 0. Right? And then a few more test cases. Let's say A and A. That should be 1. Right? And of course A and B. That should be 0. And I just try these, see how it goes. Num, distinct, SNT. Required argument X. Oh, I think I did it wrong. Do this one. Yep. Let's take a look. Run code. Rabbit. That's good. How about like this? Tons of A, and just like to say AA. That should give me a lot. 78. All right, I think this is right. Try it. Pending. Judging. Ooh, either wrong or we timed out. Probably timed out. Yep, we timed out. So, need to be smarter. Alright, so we timed out is because maybe we can cache it. Let me think. So, it says here, and if my is here, yes, we shall be able to cache it. Which means I need to return a value, all right? Okay, so if I return a value, let's say I return a value, right? And we're just gonna do return this, and we need to cache it, which is from functools import LRU cache. So I'm gonna cache this, right? LRU cache max size equals none. Now we don't need this. So how do we cache? Well, what we cache is given the preposition, right, and the current index. Actually, that is not going to work because preposition will be different. It is not preposition we need to cache. It is from the current position, right? That's the one we need to cache. So we have, like, I'll try it again. So we have lots of levels, right? We have lots of levels, and each level we have different points, right? Different points. So what I want is at a certain level, right? At a certain level, what is the total number that we can generate? Because we're from here, and we can generate all this. From here, we can generate all this, and from this, it should be the same. So, no, this is not going to work. So what we want is index. That's true. This is the index on the T. Actually, I'm going to just say that's going to be TI, right? That's the index on the T. And we need to know the index on S. So SI. So SI, TI, right? That's going to be int. So let's write it SI, TI. So we have SI and TI. So this is the total number of total number of subsequences from, now I like ti and then si, from ti towards the end, and can be formed by subsequences starting from si. That's it, right? So what we want is 0, 0. That's what we want, 0 and 0, right? So in this case, we start from ti, right? We start from ti and then given it's si, right? So it's going to be 0, 0. So what is the end condition? Well, the end condition is if ti, right? If ti goes to the end and si is not at the end, then that gonna give us, yeah, so the end result. Okay, what is the end result? The end result is ti reach the end, right? Ti reach the end. And we can probably also, let's also remove some of the edge cases. If ti reach the end, right, and si has not reached the end, right, and that's good, right? That's good. That's like a different way of. So what we're saying is the total number. So to know the total number will be to know everything below me, right? Everything below me. So it's a ti plus 1, and si, like the next level, si plus, right? So we want to know all of that, right? All of that. And then when we have that, then that's good, right? Then that's good. Okay, so what is the end condition, the edge case? Well, the edge case is move one level down. So whenever we hit, then we're gonna give you 0, right? So when ti is equal to this, right? When ti is equal to this, or si, right? So one of them, if this or si is equal to len s, so one of them go beyond, right? One of them go beyond, that will return 0, right? That will return 0. Otherwise, what's going to happen is going to be the total number from here, right? From here, moving on to the next one, so just ti plus 1. So it's going to be ti plus 1. That's going to be dfs ti plus 1. And then every single one, right? Every single one. So the rest is going to equal to 0. And for NSI, next SI in BI is going to equal to bisect right. I should not have deleted. BI should equal to this. I think this is still correct. Right, this is just still correct. Let me change a little bit. So BI is just the index, right? So it can be position TTI, right? So that's that. And what we're going to search for is TI, is SI, right? SI. We're going to search for the next level, right? The next level. Next level is TI plus 1, right? So the next level, that is the next level letter, right? The next level letter, and we find its position, because all the position, and we want to find the current position as SI. When we find the ones larger than SI, so which we use this, which will give us the BI, which is the next one. Okay, so with this, right, with this, what we're going to do is for the next SI, actually not next SI, it's just for I in range from BI all the way to len position T, TI plus 1. So that's the all the possible, right? All the possible. So all the possible of them, what we're going to do is do TI plus 1 as the next level, and I, that's going to give us the total number. And when they res plus equal this, and then they return res. And because we cache, so all of them only calculated once. Alright, which means this probably have to happen not here. Right? So what we're going to do is we'll handle TI plus 1. So we cannot do TI plus 1. So TI, if already at the end, so we cannot do. So what happens if TI is at the end? Well, if TI is at the end, then whatever SI I have, that's going to return 1, right? So let's say if TI is equal to len T minus 1, right? So which means we are at the last row, and then any SI that I have encountered, any SI I encountered, that's going to be return 1, right? Well, we have to also handle if TI does not reach the end, but SI is equal to len S, right? So SI has reached the end. Will this even be possible for it to reach beyond the end? I don't think so, because we are limiting here, right? We're limiting, which means I don't think this is possible. I think this is all we need, because we're limiting. We're not going to go beyond S, right? The I will not go beyond S. I have some issues. Okay, it's not correct. Let's focus on. Let's focus on the first one. Just kind of see what went wrong there. So binary search for TI plus 1. Right? So again, if this happens, so T reach the end, and that means from this position and this whatever SI position that we have at the moment, that's going to return 1, no problem, right? But if TI is not at the end, which means it's not the last row, and we have an SI, right? We have an SI. Hold on. SI is SI. Nobody says SI is the matching one, right? That's the problem. That's the problem. Are we saying SI is going to be the matching one? Yes, that's what we're saying. We say SI is going to be the matching one. SI is going to be the letter that matches TI, right? And then we can use all this. We can use the binary search. That's what makes it work, right? We can use the binary search for this, which means we should not start. Hold on. What I'm saying is we're gonna start from the first matching, right? That's what we're talking about. We're gonna start from the first matching, and then we're gonna go to the next one. So we start from the first matching. Let's say with some 0, 0, right? And then bisect, right? Position. So position 1, which is gonna be A, and 0, which is gonna give us 0, right? So we're gonna do I. That's not SI. That's not SI. It should be This is SI. It's this one. And of course, this is going to be TI plus 1, right? Maybe TI plus 1. That is the next position. So if we do this, now we pass, right? Now we pass. But now we fail on this. Why do we fail on this? Well, we fail on this because the result is 3. Interesting. So first one, right, and then second, binary search from here, everything that we can match. And I go through all of them from BI to len, this, right? So we go through every single one of them. That's the next SI, which matches to TI plus 1. Yeah. Hold on. Why is this one not right? Let's print TI plus 1 and this one. Right? So we're talking about 1, 1, yeah. And then it's gonna be 2. 2 is in G, so 0, 1, 2, 0, 1, 2, 3. So we have this. 2, 3. Alright? That's good. And then we have 2, 6. 0, 1, 2, 3, 4, 5, 6. Yeah, 2, 6. That's good. So we're done. We're coming back to 1, and we have 1, 5. And we have 2, 6. Oh, I see. I forgot to. No, we have to go. Ooh. What should we do here? Because we have to find. We forgot to match the B. Forgot to match the B. So this has to be. Let's see. So T. So the T has to be -1. Nope. T -1 is not right. T -1. I thought T -1. T -1 and this -1. How about this? There we go. So both -1, right? And then when we start searching, we will be able to find it. Okay, so let's try this. Supposedly we have cached everything. All right. So this is the cached version. And of course, we're gonna run this. Let's see. Pending. Finish. Yep. I think this one shall be right. Pending. Judging. Oh, come on. Are we timed out again? Oh, we timed out again. How? We cached everything. I don't understand. Don't tell me it's a 0. I mean, how should I say it? maybe. I don't know. I'm gonna cheat. Let's see. Let's say return 0. Let's say is it 0? Yeah, it's 0. So what I think is we are lacking a check at the beginning, right? I think that's what we're lacking. Check at the beginning, which we just say let's say M, right? M. Now just say if len s is smaller than len t, return 0. And that is the case here. No, wait, what? That's not what it is? Oh, that probably is a B hidden. There we go. Ah. Alright. Yeah. I realize what it is. No, that's not the case. Oh, we can leave it here. We can leave it here. Alright. So, caching. That's OMN. That's 1000 times 1000. And it says, nope, can't do that. So it's still, which means there gotta be a even better way, right? Even better way. Huh. Okay, so we want an even better way. I mean, one way we can do, we try to not to do the recursion. That might help, might. But I don't really think that's the case, though. Alright, just for this in particular, right? For this in particular, what happened? Oh, what happened is, for every one of this, right? For every one of this, we binary search, which just go to the next one. Right, we just go to the next one, and hold on. This, I handle this, right? And then handle. Okay, and then what? And then we come back. Let's go here. So we binary search for the next possibility. This one. Okay, but all this is all done. It's all done. Let's try bottom up. Let's try bottom up. So if we try bottom up, what do we have? Again, we have a bunch of rows, right? A bunch of rows, and then we have some positions, whatever position that we have. And then the bottom row, right? They'll all be ones, right? There's no problem. They'll all be ones on the bottom. Now, on the row above it, right? What we can do is, instead of recording all the one, maybe we use prefix sum, right? We can use prefix sum because on this level, let's say B and B, right? So this B, we need a sum of all ways from A to the end. Like over A, we have A all the way to the end. And from this B is going to be this A all the way to the end. So if we have all the way to the end already, then we don't have to iterate, right? So this one will not be a range. Okay. So if we build bottom up, yeah, let's build bottom up. So the last one is going to be G, right? So all the positions are going to be 1000. We can do, let's just make a matrix, right? A matrix, just go this one. A full matrix, right? Full matrix, it can be 3 rows by 1, 2, 3, 4, 5, 6, 7 columns. So 1, 2, 3, 4, 5, 6. So 7 columns, and everybody can initialize as 0. And we're gonna go on the last, right? So we're gonna put BA, BG, BAG. Right? So the last row, on the last row, we're gonna go, all the matching gonna be 1, right? So this is gonna be 1, and this one will be 1. No, it's not gonna be 1. Huh. It's gonna be actually be 2, right? Yeah, it's actually be 2 because we're gonna do prefix sum from this one going back, so it'd be 2. Now A, right? Now we go A. A, the last A is here, so the last A, we're gonna go look for the G, and that's 1, which means this A, right? This A gonna record 1 in one way, and then we have this A. Now this A gonna look for this G, and this G actually is 2, so this A gonna get 2, and we know plus this A, so this actually gonna get 3, right? That's gonna get 3, and then on the top, we have this B gonna get 1, right? This B gonna get 1, and this B is going to get 1, but we have already 1, so this B gonna get 2, and 1000 by 1000, we can afford to make a matrix, a huge matrix, but we don't need to have a huge matrix, all right? Because we're only using the data on the row below us, so we can actually do ON, right? Which is going to be 1000, which is one row. One row is sufficient. Think about it again. If two rows is sufficient, right? 2 rows is sufficient. Yes, I think 2 rows is sufficient. All right, again, third time a charm. So again, this one is necessary. We're going to bottom up, so we're not going to do any of this. That's fine because we have this. So we're going to have DP, right? So DP, we just need 1. So 0 times len s, right? And let's just throw this one here. Edge cases to make things easier. We don't have to worry about anything like that. So DP is this, right? And then what we're gonna do is the last T, right? The last T, that is going to be. Can we just like make them together? Let me think. Well, so if we go, say, one level lower, let's just make it, which is everything, right? Everything. So it's gonna be filling the last row, filling the last row, filling the last row, because I need to use binary search to find the 1. Right? That's what we want, the binary search to find the 1. But on those, we don't have binary search. Maybe we do. Because what we need is just an index, right? An index. So if the next one, we don't have a next one. We don't have a next one. So let's just do this. So we're going to be 4. So we're going to fill in the last row, just for I in position T minus 1, right? For I in position T minus 1. And then they're going to be all 0. right? For I in position t minus 1 as the last letter. I'm going to find all of them. And actually this one is going to be reversed, right? It's not going to be reversed. I'm going to say dpi, right? dpi is going to be equal to, hold a sec. So next dp, so that should be the previous. What am I actually going for here? This? No, I need the index. I need the index, not the actual value. So for I in range, len, position, t minus 1, right? Minus 1, minus 1, minus 1. So that's index for position t this, right? And then what we're going to do is dp position t minus 1 I, right? That is going to be the last index. And that index put into dp, it should equal to 1 plus dp position t, last letter. Plus this to make things easier. All right, so letter position. Let's call letter position. Letter position. All of this is going to turn into letter position. Right. So this is going to be dp letter position. This equal to dp letter position I plus 1, the next one, right? Equals this, and if I is smaller than the last one, smaller than this, right? If I is smaller than this, else 0. Right, so that is the fill out. That is to fill out the last row. And then, so we're going to say this is to fill out the last row. The last row. Now, we're going to do for j, right? Actually, we're going to do I again. Oh, then this one actually going to be j. Yes, this one going to be j. So this is representing columns, right? Representing columns. Now we're going to say for I in range, len t for minus 1, minus 2. This is handling minus 1 already. So minus 2, minus 1, minus 1. Yeah, let's just do this. Fill out. And this one is going to be fill out the remaining rows, right? So we're going to I. What we're going to do is we're going to find something. Again, I'm going to say for j, right, in range. Again, letter position equal to position, right? Position t I, right? And in range, len letter position -1, -1, -1 from back to the front, right? Now what we're gonna do is to find, using binary search, right, to find the actual position. So how do we do the binary search? So we have the J, the other position, so we can say SI is going to be letter position, right, letter position J, right? That is the SI. Now using the SI, I can find, and then we have the same thing. I have a BI. So I'll just copy and paste this one. So BI is going to equal to binary search position T, right? And it's going to be I plus 1. All right, I plus 1 is the next level. And SI, so that's going to find the BI, right? And what we're going to do is to have it's what if like, hold on, what if like it's larger? It's larger. Huh. But not really large. It's like if like we don't have anything. Right? We don't have anything. If we don't have anything, then what we will find is the BI is going to be outside the range, right? BI going to be outside the range. So if BI is outside the range, then it's going to be nothing. Yeah. And if BI is not outside the range, so that is going to be let's see, so it would be DP. No, not DP. So for everything, we're going to have a temp that equals 0 times minus, right? That's a temp. And now we have the BI, right? And we say if BI is smaller than len letter position, no, not letter positions, position T I plus 1, right? If BI is smaller than this, right, that means we have something. So if BI is smaller than this, then we can find the value. So we find the value is going to be DP position T plus 1, I plus 1, right? This position BI, right? And that one is the cumulative sum, right? This is the cumulative sum. So it will be this sum, all right, plus temp, be plus temp, letter position, J plus 1, right? J plus 1. So DP letter position J plus equal to, right? Well, it's actually no plus equal. We only handle it once, right? So it's just going to be equal to this if J is smaller than len letter position minus 1, else 0. So the same as here. We're going to add this. I mean, in this case, I feel like yeah, so that is that. So if bi is smaller than this, then we can update the dp. It's actually not dp. It's not dp. This is all temp. This is going to be temp. Right, this is dp. Temp equals, this is dp, which is like the one level below us. And there's another temp that's to make it accumulative. So for I in this, for j in this, so we handle this. Land position. Isn't this the same as this? Huh. Hold on. We do have to get every single one, right? So isn't this the same? What we're trying to do, is, so for each layer, right, I only need to go once, and then once. So like in here, I don't have to adding everything. I just looking for here. What about this one? This one, I in binary search, right? Or binary search, all of them, we find it, and then we're gonna add everything. We add this. Here we're gonna add this. We're looking for this, looking for this. And this is the same. This is the same. I think this is the same as this one. I honestly don't think this one's improving any. I thought I'm improving, but it's not. I thought by, hold on, let me think again. So we have this. If we don't do cumulative sum, so we have to go here. So like every level, like this level, we have to add, let's say add everything, right? And this level, we have to add everything again. And this level, we have to add everything again. So for each one of these, we go this, each one, and I go each one, and I have to add everything. But this is still ONN. Plus, we have a binary search to play a role. I don't know if this is going to be any easier, man. Yeah, imagine in this, we still have to go from the last one. Right, we fill out the last row, and I'll go here, every single one. We binary search, right? So we find this, and then the next one, we have to add this, and then plus this, and this one, add this plus this, right? Every single level, we have to do all this. Every single level, we have to do all this. Yeah, I don't think this one is making it any easier. So like return. And when we're done, let's say dp equals temp, and then we return dp 0. Yeah, that's not even pass. That's not even correct. No. And even if this one works, that's OMN. Probably it's still going to time out. And it's not even correct. That's probably because of this. So let's say we add parentheses. Yeah, but hold on. Let me let's time out. Let's run this code. See if it passes. Oh, that is interesting. What are you saying? This one will pass? Uh-oh. Got a wrong answer. Got a wrong answer. It passed the other one, so this one might have. I don't know. I thought it's the same thing. Yeah, let's handle this one first. Should be 5. What do we get? Got 0. Jeez. Come on, man. Oh, what is the cluster? S. What are we gonna do here? Let's see. The last row. Last row is 1. Ba 2, 3, ba 4, 5. Yep. And then second, temp equals this, right? Oh, it's not DP0. Holy guacamole. Holy guacamole. That should be DP. DP position T0, right? DP position T0. T0, position T0. 0. Yeah. I wonder, like, what if I have like this? That should be 0, right? And it will be indexed out of range. Huh. I need a way to check, like they do fit. How do I check that? Well, what we can check is that will be nothing, right? So, and then we're gonna say I len t, that's fine, and then this, so if it's not working for one of this, it will not have, so DP is gonna be 0. So we just need to make sure that it does exist. So position this does not exist, right? It does not exist, which means I'm going to return 0 if not position T0, else this. Okay. Okay. Make a little more change to make it more readable. Letter to fill out the first row. Then we have letter position is the letter position of the current, right? Current letter position, and when it says len letter position for everyone in the current letter position, and the S position right? We can get it at the S position. The binary search is the binary search index for the next one. And we say if it exists, then temp letter position the current one equals to the DP, which is the next level. This is BI, which is actually this is the SI of the next letter, right? So we get the cumulative sum, and then with a plus, it's going to be temp as the next one. If j is smaller, right? If not, it'll be 0. Okay. So I think let's try this one. Again, I'm going to try this first. See if this one still works. Should, right? Alright. Let's try it again. Pending, judging. This one we pass. So it is faster. I don't know. Like earlier when I was thinking, the one that we failed, right? The one that we failed. How did we do? The one that we failed, we for each row, right? We pick a one, and then the next row, we find every single one of them. We add this, right? And then for each one, we add, which means the runtime is OM for all the rows, and ON for each column, and ON squared. OMN squared. And this is OMN. This is OMN. I do wish that this can be combined with this because they look very, very similar. Right? But the last row is easier to reason with. Right? The last row is easier to reason with. Oh, can I make it simpler? I mean, I don't have to write this. I can just... You know what? I think it's actually easier for me to reason if I just swap this with what it's supposed to be. It's gonna look long, right? But it makes more sense. So I know what I'm actually doing. So it's DP position. I can see, okay, T minus 1 is the last letter. Position this is the array of the indices, right? And then J plus 1 is the next one in this array of indices, and DP that is the DP. So that's actually make it easier for me to understand. So we don't need this. This, and this, right? Yeah. But SI is used only once, so SI only need... So we understand what this one means. This is just I, the current row, right? This is the current letter of consideration, and we find the J because we go one by one, right? We go one by one, and then we do bisect. Right? Bisect. This is a bisect index. This is needed. So here is this saying. So the saying is first find the indices, right, for all letters in S. Then we go from the last letter in T to the beginning, right? To the beginning. For each letter, right? For each letter, we find. Right, for each letter, we find all the indices of the letter in S. We go from the last index, towards the beginning, right? Say we are at Ti and Si, where Ti equals Si, right? And then the total number of subsequences, right? The total number of subsequences that forms Ti, right? That forms PTI from SI, SSI is yeah, this is actually a better way. So let's define dp, right? Ti si as the number of subsequences formed from number of subsequences that form T this from S this, right? Where Ti is equal to SSI, right? So now we can say going from T minus 1 to T0, and S minus 1 to S0, we have dp Ti minus 1 Ti minus 1 Si, right? Ti minus 1 Si equal to dpti, right? S S, I don't know, how should I do this? Sk, right? Sk plus dp Ti S k plus 1, k plus 1. Not really Sk plus 1. Sk1, Sk2, right? Sk1, Sk2 plus plus dp Ti and Sk, I don't know, Skm, right? Where Si is smaller than Sk1, smaller than Sk2, smaller than smaller than Skm, and Ti, right, is equal to Sk1 equal to Sk2 equal to equal to Skm. This we can speed up. We can speed up this dp relationship by not computing this every single time, right? Not computing this for each ti. Instead, we can form in a cumulative sum, prefix sum, right? Prefix sum in dp ti, such that dp ti minus 1, right, si, or equal to dpti sk1, right, plus dp ti minus 1 si1. I'm going to call it si0. si1. Let's call it si0. sk0, sk1. Yeah, this will be better. Maybe sk0, sk1, right? Then sk0, sk1, and then it's be si0 equals plus dpsi1. Right. This reduces time complexity a lot. We also use binary search to find sk0. Actually, this will be sk0. sk0. Binary search to find sk0 from si0. Right. So the time complexity is O M N log n, right? Where m is the length of t and n the length of of s. Okay, so what's our oof, pretty bad. We have 669 milliseconds, right? 669 milliseconds, or 669 milliseconds, and a 6% ranking. All right, so solved it, but based on the runtime, it looks pretty bad. Maybe binary search is giving us too much overhead? I don't think so, though. I mean, it is possible that if we run a check before we do all this, right? So let's say we run it. So we run this check, right? And then we also run we'll check everything. If they're in it, if there's anything that's not in it, then it's going to be 0. Let's try that. So hold on, I'll be back. Alright, I'm back. Alright, let's check the, oh, we're talking about to speed it up, right? So, to speed it up, we can just do a pre-check. How do we pre-check? Why just do a set and set, right? Let's see, I can just do a set minus set. Like this, set, let's say, ABC, right? Minus set, who minus whom? A, B, C, C, B, D. What is, yeah, so this should be an empty set, right? So if we have anything that's not belonging, so we can do a set with if this or set T minus set S, right? Or not set T minus set S. Or explicit. Alright, so yeah, let's try this. I ain't right. Wait. How? Set T minus set S. Oh wait, no, it's not. It is. It's this. There we go. So I'll have some comments right there as well. Alright, try this, see if it's faster. Do a little set operation. Look at that! Look at that! With a set operation, our runtime from 669 milliseconds shrank to 40. Come on, it's more than 10 times. It's 15 times faster. 15. Just one line. 15 times faster. Alright, so so update by pre-checking, right? By pre-checking pre-checking whether T is possible, right? Is possible to be how should I say it? Whether all letters in T exist in S, we shrink the runtime down, runtime to 40 milliseconds. 40 milliseconds. Yep. This is the trick, I guess, to make it faster. If you think about it, it does, because T and S, they are only 1,000 letters long. So set minus set is very fast. It's lightning fast. All right. So this one can eliminate like the last test case that we got trouble with. All right. You know what? I'm pretty sure if we're using this scheme with the method we used earlier, it probably will pass as well. But I do think this is faster. This is faster. Okay, now let's see. In that case, we probably don't need binary search. I mean, if you think about it, right? The runtime, yeah, we probably don't need binary search. Oh, but binary search only adds just a little bit complexity. Does it add a little bit complexity, or it adds a lot of complexity? If it's not binary search, it's going to be from start, right? From start, and then we have to add another condition. So it's the same. We'll just leave it here. All right, now with a much better runtime, I have confidence to go into check it out. See what the bed 115. I would probably have done it. 115. Yeah, I have a hunch that we have done this before. Let's see if we've done this before. Nope. Nope. We have not done this before. First time. 115. Short DP solution. Oh my goodness, you gotta be shitting me. I'm sorry for the language, but what the hell? Where dpij is the number of subsequences of 0 to I equal to 0 to j. Then to evaluate dpij, we need to look at two options. I minus 1j if we do not include the symbol si. If we include it, but it's only for the case when omn. I'll be back. Alright, I'm back. Nah, this is not happening. What the hell? If I is equal to minus 1, return if j equals to minus 1. What? So dpij, which is 0 to I, number of subsequence from 0 to I, 0 to j, equals I minus 1, j. So dp I minus 1, so s to I minus 1 and j, right? The number of that plus, so we have the number of this and the number of this and then this, right? the number of subsequences here and here, and we have another total number, right? And then we extend one more. Now what happens? So whatever this number, if these two are not the same, so if I and j are not the same, then it's not going to change. That is true. It's not going to change. If they are the same, right, if the last one is the same, then it's going to be this, the previous one, the total number, right, and what the hell? What the hell? Yeah, it is correct. So this is, if you think about it, this is LCS, longest common subsequence. Right? If it's the same, we go -1, -1. If it's not the same, but we just do one of them -1. Holy guacamole. Okay, so all right. I thought mine was good. No, it was not. It bloody was not. Okay. Let's. This is from the Babichev. Super duper easy. Huh. Alright. Let's copy this. But let's try to write it ourselves. Alright, so we define dp, right? So define dp ij as the number of subsequences that form T 0 to J, right? From S 0 to I, right? So dp ij is going to equal to dp, right? I j is going to be equal to dp I minus 1j. Right, I minus 1j. Or I plus 1j. Yeah, it depends on like which direction you're thinking. They always think about, we have a chunk done already, right? Now we're gonna add an I to it. Right? Now we're gonna add an I to it. So how do we handle, right? How do we handle? So we add the same j, right? The same j. We need to compute ij, so we say, okay, this is going to be equal to I minus 1j, the total number, right? Plus 0, right? If ts I, that's actually going to be plus 1, right? This is going to be I plus 1. From si, if si is not equal to tj, right? If they're not equal, the new I added is not equal, then it's going to be the previous one. Else, it's going to be dp I minus 1, j minus 1. That is the secret. Yes, this is the secret. dpij equals the previous one, right? Whatever we have in this match. Now we add a new one, so we're going to have this plus this, right? This plus, because they're matching, so we're going to plus this. Right? Do we handle the other way? Like, let's say I and j minus 1? I and j minus 1. We don't have to handle I and j minus 1. Just say if I will consider ij, right? Consider ij. If they're the same, then it's going to be this. But not just this. We have to plus something else. If they're the same, the total number will be this. I have to plus this. But we don't plus this, because we don't plus j minus 1. Because if we plus j minus 1, we have to handle j, because we say up to j. So what we're going to do is def dp j turns an int. Right. Then what do? Then we say edge case, right? Because we pass in len s minus 1, pass in those. So we go minus 1, right? Which means, so what is dp00? Basically, that's the question, dp00. dp00 will equal to minus 1j plus 0 if 0 and 0 is not equal to 0, right? If they're equal, then it's going to be dp minus 1. Wow, how do we handle the 0 situation? Well, it could be 0 anything. So if I is minus 1, right? If I is minus 1, that means we are not matching anything. If I is minus 1, right, which means we're matching the empty space before the s. And this, if we match the empty space, then for j, if j is not minus 1, that's going to be 0, because there's no matching. But if j is minus 1 as well, that's empty space matching empty space, right? So it's going to be if I is equal to minus 1, if I equals minus 1, right, then when we return j equals minus 1, because if I is minus 1 and j is not minus 1, 0, if j is minus 1, then we're good. If j is minus 1, then we shall return 0. Because if j minus 1, that means we need to find a subsequence in S that can match nothing, which we cannot. We cannot, because S is not an empty string, so we cannot. So if j is minus 1, it's going to be 0. If I is minus 1, that means we have an empty string to start with, right? Hold on, if j is minus 1, That means we need to match an empty string. Shouldn't we return I equals -1? I is -1, which means S is an empty string, so T has to be an empty string. If it's an empty string, we can match. J is -1. Would it happen that J is -1? It's only happening in this case, right? J -1. And I will be -1. Would it happen J is -1 while I is not -1? Maybe. So if I is not -1, right? So this is actually going to be I equals -1 as well, right? But if I is -1, we already handle it. So it's only I is not -1. So if I is not -1, this one's going to return 0. That makes sense. And then the rest is going to be shall we return dp I -1 j plus si equal to tj, right, times dp I -1 j -1. And then return dp len s -1 and len t -1. Right, say so 2. Nope. There's some issues. Huh. Of course, for the cache. Why would this one be wrong? Si equal to ti, and then we're going to do this, right? Ji -1, however much. If they're not the same, which is going to be this. If they are the same, it's going to also add I -1, j -1. Yeah. Hold on. Is this one equal to 1? Oh, this should be 1 because this means I is not equal to -1, which means we have some in S, and T is an empty string. Any substring in S will form an empty string, right? We just remove everything. There we go. There we go. So this means we have S but T is empty string. No, I don't like how my explanation is. There is always one way to form an empty string from a non empty string S. Empty string T from an empty string S. And add this at the top to make it even faster. Okay, let's try it. Yep, pretty fast. Pretty darn fast. Wow. Hmm, 1, 0. Yep. MVP I plus 1. I plus 1, J plus 1. Yeah, this is the think the other way towards the end, right? So, well, 1, 0, 0 is going to be 1, right? Of this and plus this. If this is equal, then plus. Alright, that will be it for today. Well, we did solve it, so nothing too bad. But compared to the good solution, it's pretty obvious that we have a lot more to learn. Yeah, okay, it's like what, 5, 6 lines. It's all complicated. And binary search. We don't have binary search, it's all MN as well. Alright, that'll be it. I'll see you guys tomorrow.